he said a biometric, how do you guys pronounce it? The biometrics. So biometrics authentication system for an ATM machine using keypad and fingerprint scanner. That's the topic. Biometrics authentication of an automated teller machine.
Automatic teller machine.
Is it automatic or automated?
Automated.
I'm asking, is it automated or automatic?
Automated.
It's automated. Teller machine using fingerprints and passcode and keypad. Now, if you say fingerprints, this is it. So you accept fingerprint scanner, then we're going to use passcode. So if you say fingerprints, that means it's passcode. Do you understand what I just said now?
Yeah.
If I say fingerprint scanner, then I'll access the keypad. So now we're going to be talking about the module with which this and this is used. So, however, whether it's true, however you want to call it, fingerprint scanner and a keypad, or fingerprint and passcode. Now, I'm a bit kind of careful when I use the word passcode and passcode. Passcode should be a combination of alphanumeric. Passcode should just be numbers. But this one that the numbers we actually even use is a string. What do you now call it? Because it's not a number, really. So it should be password. It's password, not password. It's password. It's password. More so, it's actually a combination of alphabet and numbers, even though they are strings. Okay? Okay, so as usual, so what this user wants to do is very simple. He wants to have a now, before I go into that, there's a problem. How do we design an ATM? My responsibility while we're discussing was not to design an ATM. So I said we'll need to find a way to actually typify the use of the ATM. So we'll put there a relay and then we'll put a load. So anything will typify, so long as the load comes on, the relay switches. If it's an ATM that is there, the ATM comes on. Wherever is there comes on. That's the point. Wherever is there comes on. So we just have a load, a relay to typify the ATM. Do you get it? So before we continue here, the first of course will be to actually put the system in the block diagram. It helps to tell all of the things we are going to need and not need. To prepare a block diagram, few things we need. We know we are going to require a power supply. Always. I don't fail at it. I know I'm going to need a microcontroller. That's my man. I know for sure that because fingerprint is there, I'm going to need a fingerprint scanner. Now, I told you there are various types of the fingerprint scanner that we've operated with. I've used the SM630A before. No, I think the SM630. I've used the FPM10A, which is not very different from the ZPM20XS series. Then we have the DY50. Then we have other types. Then there is this other one, I think GT11. I've used that one too. So 1, 2, 3, 4, 5. These fingerprint scanners I've actually used before. Okay, so but the one that we have used in this project is the FPM10A. So do you have this? Can I claim?
Is that ZPM or 2PM?
ZPM. It's ZFM. It's ZFM. It's ZFM.
20 XS.
20 XS series, which means there's some part numbers not so clear. Now, truth is, based on the part number, if you get the material, the data sheet for the specific one you bought, which is something I advocate, that when you pick up a sensor or any device for that matter, it is very important that you pick up the data sheet and hear what the manufacturer has to say. It is in the manufacturer data sheet you're going to get its power requirements, whether it's operated with 3.3 volt or 5 volts. Current requirements, 100 milliamp, 150 milliamp, 1 amp, 1.5 amps. You're going to know the number of prints it can store. Then how you communicate with it. Its communication means whether it is UART, whether it is I2C, whether it is SPI, whether it's one wire, wherever. Are you with me? So it's from the manufacturer data sheet you get all of that. So that's why it's important that when you eventually settle for either of the scanners you want to use, it will be important that you do what? You get the material, the data sheet. So the one we have here is the LPM 10. I also know that I'm going to need a keypad. Now, there's a difference between a keyboard and a keypad. You need to understand that. And we had already established here that the keypads you're going to find in the market are going to be the Matrix Keypad. And we'll discuss why it's Matrix. Hope you remember. Were you in that class? You should be in that class. I beg you were in that class. We said, okay, don't worry, we'll get to all of that. So we have a keypad. We have a 4x4 Matrix Keypad. Now, I didn't say keyboard. I said keypad. I know that we're going to require a display. We're going to have an LCD display. We have a 20x4 LCD. What else we have there? We have a buzzer. Remember the word buzzer? I didn't say speaker. I said buzzer. What else we have there? We have indicators. We have at least 2 indicators there. 2 light emitting diodes. 2 indicators. We have one for change code indicator. We have another one for the load. The load indicator. Then we have the load itself. We have the load. Actually, it's a relay. Let's leave it there. This is what we have. Then we know that our power supply is going to feed all of this. Our power supply is going to feed the keypad. So this is the block diagram for the project. Can we continue? Yeah. Right. Okay. Is it clear? So, what will we do? For us to have a very good understanding of the project, we have to actually explain these blocks, and from these blocks, deduce the circuit diagrams for each block, and then we'll be done explaining the project. First is power supply. I'd always maintain that before you go, it's like having 4 boys in this room, 4 boys in the house, and then you want to cook. And then you are not taking into cognizance how much of food you will require, he will require, and we all will require. They just went and bought 1 drink of rice. Guy. Only me God will finish it. And the rest of you will be lucky. So there's this book, Leaders Eat Last. Have you read that book? Yeah, I hate first.
Not Nigeria.
No, it's not my weather. I eat first. So when I eat first, if it's poisonous, you will know. So you want to eat it. I play the leadership role. If it's sweet, I will know. I'll tell you. Then you can then taste it. I mean, that will even heighten your interest and your desire to want to eat it and your taste bud. So that's leadership. Try to eat first.
You leave the way.
But the issue is, the person who wrote the book was saying from this, let me tell you from what angle he was saying. He said, when you do business, I mean, you pay your vendors, you pay NEPA, you pay for electricity, you pay for space, accommodation, your landlord gets paid, you pay your staffs, they all get paid. Then the bank get paid. Bank remove their charges, blah, 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 and what's left? Then the company get paid. It is then you then get paid. So you get paid last. It's good. Guy, I get paid first. Then I'm motivated to do the job so that the company can get paid, the bank can get paid, and every other person can get paid. Guy, if I don't spend part of the money, I'm not motivated. If I don't do the job, then nobody gets paid. You get it? Alright. So who gets paid?
Me.
Thank you. So that guy, I think it's something Simon, but it's his name. Eh?
Because I'm the center of it.
Yeah. Tell us your own argument. Who should get paid first?
I don't want to get paid.
Hmm?
I don't want to get paid.
Why?
Because I'm a main guy. If I crumb, nothing will happen.
Who tell you? Then your business is not structured. Your business is structured. If you crumble, the business continues.
Why?
Because the business should not be one around you.
I don't want the business, I don't want around.
Okay, so you have designers. Somebody brought the job. You are not the one that was called. Maybe the desk, the secretary desk was called for the job. The conversation was done. You were informed. You said, okay, this price is good for it, and then you approve it. The company account is paid, so the company account gets paid first, get the money, and then you look at it and say, okay, David, draw a circuit diagram. Emmanuel, please write the code. Ayo, please, you do the PCB. You've worked. I don't even have to be here for that to happen. You guys are doing pretty well already. Don't you see? So the business is not around me anymore. It's around you. It's structured. So I can actually go back to my mountain climbing in Oyo State or wherever it is I went the other time. Just repeat it. You get it? Alright, so this is what we have. So before you discuss power supply, you need to take cognizance the power requirement of every guy you're going to need. That should inform what your power supply should be. Because if you don't take into cognizance what their power requirement is, when I mean power requirement, you put it in current requirement, then you go for you to use. For instance, the DY50 actually runs at 3.3 volts. But this can actually run at 5 volts. So if you've not known that, or let's assume it was the DY50 we had to use, and we didn't plan a 3.3 volts, how would we have dropped the 5 volts to 3.3? We would have just ended up burning it. Did you get the point? Okay, so let's do a quick one now. We know that our FPM runs on 5 volts DC. We have the data sheet to confirm that. Our Matrix Keypad is connected to the microcontroller. The microcontroller is the one that actually, of course, there's supposed to be a pull-up on a number of the pins. I think 4 of them. I think the last 2, but there. So microcontroller powers it, so we expect 5 volts. The microcontroller itself runs at 5 volts at what? 25 milliamp per pin. The relay, I chose a 5 volt relay this time. When I mean 5 volt relay, I meant the coil of the relay is what? Is 5 volts. So I had a 5 volt relay. These are indicators, light emitting diode, so we're talking 5 volts. The booster itself is 12 volts. The LCD is 5 volts. So if you look at the assembly, you can tell that the 2 power supplies you need are what? 12 volts and 5 volt DC. Now, since the system is going to run on battery, there needs to be a way with which that battery is charged. Now, I did not actually plan a charging circuit into it, so all I just do is buy an adapter and attach to it. But if there was, we were going to actually plan for that, what we would have done, which is very simple, and this is the diagram, so please watch it. That's, you check it out. For the power supply, what we would have done would have been this. We would have gotten a transformer. Don't forget, a 220/240 volt transformer. We also need to be sure that the transformer is such that can supply the current requirement as required. That the system requires. The system needs it. From quick observation that we've done this morning, we know that this guy sources more than 150 milliamp, like you said. The assumption for me, if you ask me, is that this guy maybe uses around maybe 1.5 amps to come on or to operate. So let's assume that. If we assume that this guy is 1.5 amps, of course, we know that this one's, the line that will go at maybe 10 milliamp. Your relay should not be more than maybe 80 ohms. You divide 80 ohms, or 30, like 30 or 300 ohms. 30 ohms divided by the 5 that is real. You should be able to tell the current that is playing. My point is, if we get a 1.5 amps transformer, we are good. The transformer, of course, is a step-down transformer. From this end, is supposed to be a switch. That goes into what? A bridge rectifier. Don't forget. And then you have this assembly. Don't forget, you should have a capacitor here that filters the ripple. And I've told you that for voltage not greater than 12 volts, your 1000 microfarad 25 volt is okay. Don't forget, that the working voltage rating of the capacitor should actually be higher than what the voltage across it. So we are expecting both 12 volts here, then the 25 volts working with the capacitor should be about 1000 microfarad. This can then be sent into the 7805. Now, the guy that requires 12, which is the buzzer, will have gotten the plus 12 volts this way. Alright? So the common, and then you have another capacitor here. This is usually 100 microfarad, 16 volts. And then the guy that requires plus 5 volts this way can get it here. Does it make sense? If we are using an LCD, now please look up, and this is very important. Your voltage regulator will not supply more than 1 amp. So if we expect more than 1 amp here, which means we want all the current that this transformer can give. Now I forgot to tell you this. The battery, are you with me? Should be somewhere here. So which means this switch should not be here. This switch should be here. No. The switch is here is not good. It means this guy will not be charging. The switch should be here. Does it make sense? The idea is that so that once there's NEPA input here, the battery is always charging. And that if you don't close this switch, voltage does not cross it. Now when NEPA is not available, this battery is what will power this guy. And don't forget, there should be a diode there. For what? What is the work of this diode? So that this battery will know what to discharge. But the implication also is that whoever charging voltage that needs to charge the battery will have gone down by what? 0.6 volts. If this was a silicon controlled rectifier, does it make sense? And we always assume that there should be a 1N007. Now, if we expect more than 1 amp here, then we cannot use 1N4007 here. Ayo, don't close your eyes. Even though this transformer can supply us 1.5 amps, this diode do not allow more than 1 amp to flow through to charge this diode, this battery. And so you are not going to get more than 1 amp here too. So there will be no difference between the current that is available here and the current that is available here. But because we intend to try to amplify this current, amplify that current will mean that we need all the current that is coming from you, all the current available from the battery, unless we tap before the battery. So it wouldn't make sense. It wouldn't matter. Let me show you what that means. Now there's plus 5 volts here at this end. If I need to amplify current, what I simply need to do is to take this place to the base of the transistor and take the collector of that transistor to this place. So the output of the transistor, which is, so this is the collector, this is the base, this is the emitter. All this transistor TIP51, this place is now then fitted with my 100 microfarad 16 volts. This is where I'm going to get my plus 5 volts, not here anymore. Does it make sense? But look at it, the collector of the transistor came back to the input voltage, such that the current that is available, don't forget, the battery is going to have enormous amount of current because it's a battery. Even though the number of it that you draw is directly proportional to the rate at which it flattens, but it is there. So it's going to go through this transistor to this place, through the transistor. Before now, usually I put a resistor here and we do some calculations. I've actually taught him that before. Maybe not now, take it later, but just have it at the back of your mind. Now what happened is this. What we do is that we calculate we put a resistor here and calculate to a certain point where this transistor is the one that is supplying the current. It is when the current overshoots that setup that this transistor turns on and begin to produce the excess. We can say, since this guy can produce 1 amp, let's set a diode, a resistor that allows it to only supply to 500 milliamp. So at 500 milliamp, the voltage that is going to be at the base of this transistor will not be enough to turn it on. But the moment the user here or the load begins to require more than 500 milliamp, it means that more voltage is going to have to flow through that place. So in that, but then what will happen afterward is that this transistor turns on and then begin to supply the extra on the 500 milliamp that this one was initially producing. Will now be sourced from here. Are you getting what I'm saying? That's what usually happens. But since there is no resistor there doing that limitation, what happens is that the moment you turn it on, this guy is turned on immediately. So that whatever current you need is not being sourced from this guy anymore, it's sourced from this guy. Do you get it? There are 2 ways. If you put a limiting resistor here to set when this man is turned on, what happens is that the current that will be required before this man is turned on will be produced by this man. So if this man is set, the 7805 is set to produce only 1 amp, there's no need to stop it from producing any current. Just so you know what, work until more than 500 milliamp is required, or maybe more than 700. Turn on after 700 milliamp. That's turn this man on maybe after 800 milliamp. That way, if the load does not require more than that set current, this power will not be turned on. This is what will be producing the current. Until that threshold is reached and passed or exceeded, that's when this man then turns on. But if you connect it directly like this, then you are taking that work from this man to this guy. And based on the type of transistor you use here, you can get sometimes as high as 10 amps here, depending on the HFE of this transistor. Again, what is HFE and gain? We'll see that when we now begin to discuss more transistor or on a regulated power supply with current amplification. Does it make sense? Am I communicated? No. Right. So you look at it again. The collector must be connected to an input source that's infinite amount of current to supply. Please look up. What that means is this: if the battery was not here, and it was only this transformer you were using, and you already have a diode there, 1F4007, even though you have placed this transistor here, the collector of the transistor here, this guy is not still going to produce more than 1 amp, even though it can deliver up to 10 amps to you. Why? Because from the source itself cannot actually produce more than 1 amp. Why? Not because it's only having 1 amp, it's because this diode is there to only allow what? 1 amp to get in. So if you want to take advantage of the 1.5 amps that this transformer is is set to deliver, then you have to change this diode to what? A bigger one. And the next one you could have shown would be what? The 1N54.8. Is it 58 or 54.8? 54.8. This one can stand up to what? How many amps?
amps.
3 amps. Thank you very much. Does it make sense? Does it make sense? But since the battery is here, and you add 1N4007 here, what this will just do is just to limit the current that goes to this battery to 1 amp. So it's safe for the battery. Typically, a battery should not be charged with more than 10% of its rated amp hour. Now, if the battery is rated 7.5 Ah, 10% of this is 0.75. So approximately you're looking at maybe 0.8 amps. Is what this battery should be used to charge. So having a 1N4007 there is best. Because at most, even if you do another, what do you call it? Rounding up, you should not get more than what? 1 amp. But if you use the 1N54 heat, you're going to get 3 amps pulling in there. That is if the transformer can deliver it. But since the transformer itself cannot deliver more than 1.5 amps, it will be best to leave this guy at what? 1N4007 to limit 1 amp charging current to this place. What then happens is that when this one, when the load now needs more current than the 1 amp that this guy can give, the battery here will be the one supplying it. So the battery is not being fully overcharged, truly overcharged, or really being overcharged while you are getting the amount of current from them. So this is what I would have done.
Wait, but okay, that is if the battery can supply it.
Of course, the battery will be able to supply it. Yes. At whatever load, at whatever current that your load requires, one, if it has that capacitance, or at the current that this transistor can allow. So that's why you choose this transistor carefully in choosing it. Are you with me? Now, the amount of current you draw from a battery will not really matter. What you should know is that if it supplies it, it drains quickly. So even those small 12-volt microphone battery might be able to just supply you 2 amps at once. Because it's a battery. And just flatten it out. You get it. So this is what our power supply for them should be. So that every module there that requires 5 volts gets the 5 volts from here. Why the one that requires 12 volts get the 12 volts from here? That 12 volts will be after the switch. Which is the 12 volts is here. So that if the switch is open, then everything on the board is completely off. Everything. Don't forget, this is your battery. Does it make sense?
Yeah.
Hi, Clint. Now, another thing that you should also know is, please look up. Because we are actually using 4 diodes to create our bridge rectifier, if we are using 1N4007, don't forget that what it means is that not more than 1 amp can actually be used. And having this man this way too, not more than 1 amp will flow through it. So even if we had kept a 1N54 ATM, it would have been a waste. Because this man itself will not allow more than 1 amp to bring our wires. Because they are constituent of what? 1N4007. If that was what we did. If we had used 1N54 it would not matter. Or if you are going to market to buy a bridge rectifier, on the bridge rectifier you will find the current, the output current labeled on. So will have been written on it.
154 can it be used for big rectifier?
Any diode can be used as a bridge rectifier.
Maybe you can just start from the main source and use capacitor.
You tap from here.
Yes.
AC, you tap AC.
Yeah,
into this
diode to rectify it.
Okay, that's another point. But then the switch is here. What that means is that even when the switch is off, there's a signal going to the collector of that transistor.
Only the collector.
You got a good circuit design. unless you return the switch to this place. With this as, don't forget, it's an adapter that we're actually attaching to our own system. We're saying if we were to design the scheduling circuit for it, is this. Alternatively, can I clear? Huh? Now, in our case, what we have, now we don't have this. What we have is an adapter on this end. We have a terminal block that sits an adapter. So when the adapter is connected with possibly a 12-volt DC adapter, powered, puts it. The battery is charged, and then when the switch is closed, it just flows. And even when the adapter is ejected from the system still works. You get it? That's what it is. Now, if we had attached this, please look up, if we had attached this transistor, the rate at which the 725 is getting out will not have happened. I'm just taking it out. Does it make sense? Because this is on whose head the load will not be on. And since it can supply the current, why should they even go? Why should they even do that? So that's not about the password, right? That's
you look out and this one on top.
Don't worry, let us keep going. We'll find out what. Now, so that's about this. Quickly, is the FPM telling? Again, if you get the data sheet, like I said, when you pick up a sensor or any module for that matter, before you use it, visit the manufacturer data sheet. Go online, use Google, find it, you'll see one. Now, from all that we gathered, it communicates using the UARTs. What is UART to? What that means is that this one will only be connected to the UART pins of the microcontroller. Those will be the pins that, so if you look at it, say this is the fingerprint scanner, it's going to have at least VDD, it's going to have GND, and it's going to have what? Maybe the RXD and the TXD. Alright? And that's all that it is. So you take this to a plus 5 volt DC, you take this to your ground, and then you take this to the TX of the controller, and you take this to the RX of your microcontroller. Does it make sense? We already established it. Now, but don't forget, we are also saying that for UART to work, your transmitting module and your microcontroller must share what? Ground. Ground. And so, I want to connect this to ground. You have already connected to what? The ground of this one. So clear? So that's all that is there. That's all you should know. The rest are information and data that tells you how to communicate with it, how to do this, how to do this, and how to do this. Which we also actually communicate to.
Means universal.
Can I continue?
Yes, sir.
I've taken this out. I've taken this out. Now, for the matrix, for the keypad, we had discussed before that what is in the keypad, or any keypad any keypad for that matter, it just switches. I would say what usually deals with, you have a switch. I don't think I need to do this again. A switch, okay, maybe a switch. So you have this. Right? That's 3, are you? Okay, let's add 1 more. So this is 1, 2, 3, 4. 1, 2, 3, 4. That's 16 switches or 16 buttons. Switches actually. And don't forget, for a switch you're going to have that's 2 ends. What it means is that if I need to actually use this switch, 16 times 2 with 32, I'm going to need 32 different wires running from this guy to the controller. If I say I take all the ground, each one to ground, that will be 32 divided by 2, which is still 16. So I'm still going to need 16 pins to the microcontroller if I need to use a switch. Now, how many pins really does the average microcontroller have? At most, maybe you have 40 pins, and you're taking 40, you're taking 16 elements. That's 2 ports, 2 full ports. I don't think you have that luxury. So what the manufacturer of these keypads have been able to create for us a Matrix Keypad is this. So what they've done, that they now created an arrangement where, please look at this well. They took all of this down here, all of this down here, all of this down here, all of this down here. Connect. Can I continue? Now they now did this. They now took all of this. Let me use this end. They took all of this to this, to this, to this. Alright? They did the same thing here. Took all of this to this, to this, to this, and out. You see it? They took all of this, this, and out. And they took all of this, so if you call this place A, B, C, D, I call this 1, 2, 3, 4. This is what happens. When you press this button, you're activating A1. When you press this button, you're activating what? A2. You activate this, and you are activating A3. This A4. This one B1, B2, B3, B4. Please, are you following how it went? Look at it very well. This will happen, which is what I told you about scanning. At one point, you off everyone and send voltage through this one. Then you read this place. If you don't find anyone, put up the voltage and put the signal here and come here to measure, to read. Don't forget, you are only inputting those voltage just per time. You are not setting all of them high at the same time. So if I put voltage here, if I find voltage here, then it's A, it must be this button. If I find it here, it must be this button. If I find it here, it must be this button. If I find it, it must be this button. If I send the signal through B, if I find it here, then it must be this man. If I find it here, it must be this man. If I find it here, it must be this man. If I find it here, it must be this man. If I send the signal through C, and I find it anywhere here, there must be any of these buttons, or either of these buttons through D. Does it make sense? We've actually done that before. That's scanning. That's basically what happened. So the rest is just user graphic interface, where you now had 1, 2, 3, A, B, C, D. Then you have 4, 5, 6, 7, 8, 9, 0, star, and hash. You get it? That's what you have on the keypad. Does it make sense? And you already know from what we discussed before that if you need to attach this to a microcontroller, you are going to need to actually have pull-ups on these pins, at least the one that is acting as input. So you're going to need 4 resistors, 10K resistors. But since your port B offers you internal pull-up, there's no need to put the keypad on any other button on the microcontroller. That's why most systems that are designed without the pull-up resistor, you have the keypad attached to what? The port B, not port D, not port A. If it's attached to any other port other than port B, then you're going to find what? The pull-up resistor there. Please, stand up. Stand up. Thank you. Does it make sense? You get it? If you find a keypad, a Matrix keypad for that matter, connected to any other pin other than port B on any given microcontroller, there will be at least 4 pull-up resistors. Because it has to act as what? As activator. So that it is low, is when the button is pressed, and it does what? And it goes out. It goes through. Thank you. Thank you. She will continue. So it's active low, not active high. Can you continue? So that's how the Matrix keypad came about. It's clear? Now that it's keypad, it's Matrix keypad, the function you're going to need to operate it will not be what? Your KBD, the what? The C, that the C or the H, you need that keypad. And in it is when you can now format the button structure. I mean, imagine you're going to buy a button that is 1, 2, 3, A, B, 4, 5, 6. It is in that keypad header file that you have that you format what the structure, the physical structure of your keypad. Does it make sense? I mean, I showed that to him while I was doing the video. So the like, right? Alright. Have you snapped it? Oh, thank you. So that's how the 4x4. Now, again, I told you guys one time when we were keypad, I said, many times when I have keypad projects to do, I just make it a 4x4. Even though I might go to market to go and get maybe a 3x4, a 4x3 Matrix keypad, I do that. The idea is, what I now do in my header file, whatever is the KBD or C file that I get, I now leave those space for the one that is not complete, I just leave it blank. So I invent that I change my mind on the design and I get a 4x4 keypad. It just still works. I get my point. The PCB already is done, so it just works. So always make it 4x4. But of course, don't forget, if it's 4x4, you need 4 on the column, you need 4 on the row. And that's itself as taking a whole port from microcontroller. Does it make sense? Alright. The other thing that is there is the LCD, and with that, and that's what I mentioned in the school before. Your LCD is simply a 20x4 LCD. 20x4 LCD, I mean, we'll discuss about that. I told you that the 4 means there's 4 lines, and then accommodate what? 20 characters. We said that the LCD pin is about 16 pins, from ground to VDD to VO, which is your contrast control, to what now? To ROS, RWEN, D1, D2, D3, down to D8, and then you have your anode and cathode for your what? For your backlights. Right? That's what that is there. Now, on your power supply, don't forget that the output of that 5 volt is when you're supposed to have what? A variable resistor. A 102, a 1K variable resistor, which you use to set your contrast control. We'll discuss all of that before. So that's how I good at that. The buzzer. The buzzer I saw that can actually come on from the 3 point something volts to 12 volts. So why should I actually not burden it? I mean, put it on my 17 to 5 again. When I'm trying to conserve current or make current available for the guys that really need it. So I can just put it directly on the 12 volt. If I'm putting it on the 12 volt, I will need to put it on the 12 volt through what? Through a transistor. You see, those things are basic. As I said, the moment you begin to learn embedded system, the circuit diagrams will almost begin to just look alike. Maybe we just few additions because of what 1 or 2 sensors we're bringing in. Maybe that thing is awesome. So which means from your microcontroller, you have a 1K resistor, you have a transistor, probably your PIC 547, and then you can have your buzzer here. Are you with me? So the 12 volt comes in. The negative side of your buzzer comes through the collector of this transistor, and the emitter of the transistor comes to 1. So when this microcontroller biases the base of this transistor, through this one key register, the buzzer gets done and then it buzzes. And we discussed that if you need to create reading, it's also possible. All you have to do is to pause the rate at which this signal comes out and goes off, comes on and goes off on the controller. Then you can create reading. Bam, 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 wherever you want. So that's how the buzzer is created. Okay. Who else is there? Okay, so now again, don't forget, I didn't forget to say that the SSD, it is a 4-line communication we're using, like the serial, which means your D4, your D8 is all used. And then now, because, and I need to actually tell you this, please look, I need to tell you something on the SSD. Now, because the keypad has taken my port B, I'm left with just port A and port C on the controller. On my port C is where my UART is. Port C, that's where the UART modules or module is. So I figured, if my keypad or my SSD requires 8 pins, is it 8 or 7? 7. We're talking RS, RW, EN, then D4, D5, D6, and D7. D7, 1, 2, 3, 4, 5, 6, 7 pins. I can't get 7 pins from port C because the port C is 8 pins, and I need to take out transmit and receive from it. What is left? 6. From that 6, the buzzer needs 1. That's many 5. Indicator takes 1, many 4. So how then do I connect the LCD? So the LCD was already connected on my port A. But pay attention. Now I don't think I'm supposed to tell you this. You're supposed to know. Please look. The port A itself can only accommodate or offer you what? 6 input output pin. And this LCD requires what? 7. So what that means is that in your LCD configuration, you are going to get rid of what? Your RW. But you need to tell it in software, otherwise it's not going to work. Don't forget, the essence of the read write is there so that in the event that you want to read from the LCD, you can change the state of that pin and read from the LCD. Then when you have to write, but at every point when you write, the state of this read write is 0. It is when you want to read that it changes to 0. But we are not reading from the LCD, we are only writing to the LCD. So why the LCD need to bother the controller? So what we did, or what I did in the design is that, of course, I took it to grant, but I now commented in his header file, which is the LCD.c file that I'm using. That I'm not using the read write. My reader has been taken to what? To grant. So what I'm left with is what? The ROS, EN, D4, D5, D6, and D7 on port A. But understand this, which is key. Your port A, there's one pin there that cannot be used as output. What pin is that? Your RA4. It's the same thing as your TOCK, your time clocking pin. It doesn't work well as output. Why? Because it's an open connector pin. What it means is that for you to see a positive output on it, you need to put a pull up on it. That's why most times in most of my designs, I only use that pin as input. If I need several inputs on the controller, I start from that pin, that TOCK. Then I can take the other input from anywhere. Because it will not serve the purpose of an output pin unless you put a pull-up, which is an extra component for me on the board. But now that it's been connected to an LCD, you have to put a 10K resistor on that pin. What that means is that my ROS will now be with my what? My ROS 0. So it's going to be my ROS 0, my RA1, RA2, RA3, RA4, and RA5. So this RA4 should go through a 10K resistor or VDD. Does it make sense? But otherwise, the LCD will not work. Again, I'm saying this I haven't taught you, I'm repeating it. It is important. It means you need to familiarize yourself with the states and the attribute and behavior of every pin you're going to be interacting, so you know how to actually use it. If you send a high through this RA4, of course the high will go, but you are not going to see it unless you put a pull-up resistor, because it's an open collector pin. Does it make sense? So I left to just say this. It's important. And don't forget that from the anode of your LCD, which should be your pin 15 of the LCD, another resistor is taken to what? To video. That way you are limiting the amount of current that the backlight is using. Those are likely going to be the two resistors you're going to find around the LCD. It's in the circuit diagram actually. Alright? Yes, clear. It is clear. If you forget it and use an output and come that is not working, you will pay caution fee, then you will pay to face again for me to answer the question. What's that?
So, since you say it's regularly an input pin.
No, it's an input output pin. It's an input output pin, but it's best used as an input pin. Best used. More importantly, be that it's also the same pin that has your timer clock in. Are you with me? That is what pin, when you need to design a counter, you need to count events. That's the pin you use, because it's attached to your timer. So you can count events and increment the timer, or as the timer as a counter within the microcontroller. Are you following me? I'm not saying that you cannot use it as an output. I'm saying it's an input-output pin, but it is primarily used, or is best used as an input pin. If you need to use it as an output pin, you should not forget to add a pull-up resistor. Imagine or assume that you're supposed to design 1 million pieces of this system, and that simple resistor you're talking about is just 10 naira, not 10 million naira. So if there was any way I could get rid of using this pull-up resistor, trust me, I will do it. If it has to be, if it's going to be commercially profitable to me. Do you get what I'm trying to say? So what I would do, or what I could do is maybe, okay, I just split the LCD. Let RA 0, 1, 2, and 3 be for data. Then I can go back to my arrow, my port C. I go and take 4 from there too, for my default to this side. Are you following? But it's not going to help my PCB layout, because the port A's are not in the same position with the port C. They are not. If you pick up the microcontroller lose those. Your port A are here. Your port B is here. Your port C begins from around pin 13, either 12 or 13, down like this. It goes from here down like this. So your port C is around this end. Your A is here, your B is here, but your C is from here down to this place. Do you get it? So if I use part of A here, it means I have to go and bring in another block here to attach that to take advantage of the port C. And PCB will be rough. So what I have done is I left the keypad here, I left the LCD here, then I brought the fingerprint scanner here, closer to the control. Did you get it? So your routing, you usually have one. Even at that, I still had close about maybe 3 or 4 or 5 jumpers on the pin, on the board. So now imagine I broke it, and I add 6 here, then I add the other 6 here, bros. Very rough. You get it? So please, if you are making use of array as an output, especially array, make sure you have what pull-up resistor. So that's that on the LCD. And
is it that from the D6 from the
array 4?
Yes. How will you do the connection, the pull-up connection?
I mean, are you supposed to be asking that kind of a question?
No, because I don't.
You don't know what the pull-up is?
I know it, but like you know, is the wire is coming from this part of the segment into the microcontroller.
Yes.
So like I know it's now exactly like an output. Also like to be sending stuff to me. Like,
you don't even understand yourself. What are you saying? Eh? Logo. This is a microcontroller. This is the LCD. Assuming that this is your RA0, RA1, RA2, RA3, RA4, and RA5. And I'm saying this is the LCD. And I'm saying you have your RAs, EM, D4, D5, D6, and D7. So what I'll do, I'm going to take this here, connect this here, connect this here, connect this here, connect this here, and connect this here. So the pull-up we're talking about is on RA4. I can take here and put through a resistor and take this to my plus 5 volts. This is a 10 kilo ohm resistor. This is the pull-up resistor. What are you talking about?
So we both input and output.
How?
Because something is entering there. Alright. I don't know, because like voltage is entering through.
Yeah, voltage is entering there. Yes, it's not an input, but voltage is really there. It's an output pin. Voltage is there. You are pulling that pin high. That's what the pull-up is. If it's pull down, it just be a resistor to ground. That's pull down. Pull up, resistor to power. Whether it's input or output. Clear? Do you understand? So it does not matter whether it is pull up, whether it is input or output. What you want to achieve is that that place needs a pull up. It needs help. It needs signal to be there. Perpetual signal. So that when it comes high or goes low, you can actually notice it. Alright? Right? Don't forget I omitted the RW because it is not in focus.
Every people reading this thing, it means that this 6 is on.
Yes, yes, yes. That is when the switch is on. And at that time too, the LCD is on. It doesn't mean it's on all the time. If the LCD puts a low there, that place goes low. You put your meter there, you're going to find the low. It's like you design the pull down and voltage is there. If you press the button, doesn't that place go low? Even though it has a pull up resistor. That's not how you call your active low. So will you not say that place is high all the time? No. It's only high when the switch is open. When the switch closes, it goes low. Except that this time, it is not taking the VDD straight to ground. It is taking it to ground through what? The resistor. You get it. That's exactly what's also going on. Can I continue? Of course. So that's that for the LCD. Again, just the way the buzzer was connected is also the way the relay is going to be connected. Now I've told you before that when a client gives you a job to do and you're not sure what your load will be, it's better you leave your relay as a switch. Let them connect wherever they want to connect them. Which means don't tamper with your normally open contact and your wiper. Leave it. Whenever they want to connect there, they will connect. For instance, that was what I did here. You have a controller, you have a resistor, a transistor, and then you have a relay. Don't forget your relay is supposed to have volts. A flywheel diode, don't forget, it's important on the coil. The coil goes to your plus 5 volt. This I told you is a 5 volt relay. And then I have my wiper connected to my normally closed contact, and I have my normally open contact. So what I did But I got a terminal block. Are you there? And I took my normally open contact to one part of the block, and I took my wiper to the other end of the block. Does it make sense? So when the relay switches, what happens is that this place and this place behaves like a switch. It's not like a switch, it becomes a switch. So if I need this to switch an AC, you can switch an AC. If I need to switch DC, you can switch DC. How do I do it? If I need it to switch an AC, please look up. It means I'm going to have an AC source, live, neutral. Then I'm going to have an AC load, say a bulb, that requires live and neutral. What I can do is to connect the neutrals together. Then from the source, I can take the live here. Then I take from here to the root. Does it make sense? So when the relay switches, what happens? The live on the source goes from this pin to this pin, and then to the load, and then the bulb comes out. Does it make sense? And it was a DC load too. It's simple. Your DC load this time is not going to be what? Positive and negative. This is going to be positive and negative. Don't let me use N, use minus B. That's all. So this is going to be my DC load. So that way, you are not really particular about what is it they want to use with the load. Just make sure the relay is there. Except that this time, the relay that is used is a what? Is a 10 amps relay, which means this contact will not be able to stand more than 10 amps. Interestingly, it is rated 10 amps at all, 240 volt AC. So which means this relay, if it's connected to an AC load, you'll be able to stand an AC load of what? 2.4 kV. Does it make sense? Does it make sense?
What is the Dell for?
It's called a flywheel diode. What happens is that, this is a magnetic or an electromechanical switch. Electromagnetic switch, not mechanical, electromagnetic switch. It has a coil in it. So what happens is that when you push it on, the coil retains some voltage. So when you withdraw voltage from this guy and the transistor goes off, there is a possibility that the coil, the voltage that's charged up with, or it has a mass, can be sent back into your controller. Are you following me? But with this flywheel diode, because the flywheel diode it blocks that back here. Instead, it is fitted and converted to this and the what? Added back to the grid. And most times, don't forget, back EMF are always negatively charged electrons, like current, actually. Do you get it? So if it's negative, of course, it can't go through this place. If it goes through this place, it's negative. It's like using your diode as back here as a what do you call it? Reverse bias. The negative will flow through, but will block the positive. On the forward bias, the positive will flow through, but will block what? The negative will receive. Did you get it? But don't forget that another good thing you should know about this is that based on the amount of EMF you intend to block here, we determine the diode you put here. So you could use the one N 4001, 4002 and the rest. But we know that 4007, that's what we stand how many volts? 8,000 volts. Does it make sense? You see the implication of some of these little details that we discussed in discussing those components of this component. They're important. The same thing with the battery, when we're using diode to actually block back EMF on the battery. Imagine the battery is 1,500 volts. That diode will go bad because it will break its avalanche voltage range and then to damage it. You get it? Which of course is your reverse bias voltage. Can we continue? So this is how the relay is connected, so that the user is not the responsibility of the user to set up a load on the output of the relay. Is it on the output of the relay? or on the contact of the relay. Are you getting this? The indicators, pretty simple. You already know how that is connected. The load indicator here is connected to the relay. Is that connected to the relay? I do that most times, so you know when relay comes on and when relay goes off. Are you getting? I do that a lot to tell when relay comes on and when relay goes off. You know how I connect it from the. I have to tell this again. Hey, don't forget we had something like this. You had this, have you? Yeah. So what I would do is to just have from this end the resistor to a light emitting diode. Now since this is 5 volts, the 330 ohms is fine here. So don't forget this place, this part of the resistor already has anode. I mean, source, I mean there's signal there, and that signal already has flown to the anode of this of this light emitting diode, isn't it? Yeah. This light emitting diode is waiting for what? Negative. Are you with me? Yeah. So it is when the base of this transistor is biased that the collector comes to the emitter, joins to ground. That's when this light emitting diode will come on. Does it make sense? Yeah. So even when the relay is not working, or say if the relay is not the type that makes sound when it closes and opens, with this diode coming on and going up, this light emitting diode going on and coming, you can tell if signal is going to the what? To the relay. So I actually put that very time. It's not important, but it's good for simulating for debugging purposes. So when I'm done with my board, I just fire this pin to see if this light comes on. If it comes on, and I listen for a click. So I know the relay is working. Are you with me? But this is if either of the contacts of this relay goes off, which is maybe because of a current restriction, you have damaged whether the normally open contact or the wiper. It does, but as long as the coil is still intact, it does not stop that relay from saving. Even when the coil is burnt, this relay is still going to be working. Why? Because the transistor is still working. Signal is still coming here, and so that this is going to be coming on and going off. But that does not also mean that this relay is working. But it's good for the debugging purpose of the button. If your circuit diagram is working the way you have actually was planned. Alright? Look up. Can we continue? That. Those are some of my tricks from my video. Hope you guys enjoyed the class. So the other one is actually from the microcontroller. The essence of that one is an event that the user wants to actually do a password reset. So when you go into change password, the light comes on, that LED comes on. And if you do not have a successful password program, it's not going to go off. But when the password has been done correctly, the LED goes off. So just to let you know that you're about to initialize a change password operation. For a previous key code failure that I didn't have LCD to them. Why the need for it? I don't have LCD to it. If you input the right code, but I made sure that on the buzzer I created a tone for every button press. When you give it the right combination, it gives a kind of tone. The welcome message, you know it's open. When you give it the wrong code, it gives you a sound. So you get used to it. So you know code demo word, more busy. You know gel. You get it. Then the indicator is there so that you know you have initiated a change password return and the rest. So the controller, again, the source of controller when we discuss that is based on several things. For instance, from the data sheet said that the fingerprint scanner has a baud rate, which means operate at I think 57,600 600. That's the baud rate. Now, if you pick up a 16 MA 7cc that you guys use, it will not be able to actually stand this baud rate at 4 MHz. But maybe it might be able to stand it at 20 MHz. Maybe. I think you should be able to start at 20 megahertz. Now, if you start at 20 megahertz, the possible problem you might have might be program and memory size issue. This project you see was something I have actually done before with 16F84A. But I wasn't using a 20 by 4 LCD, I was using a 16 by 2. And I limited the amount of information I was putting on the LCD. If you are taking your time to look at it, you see one thing that was that I did every day was that every operation or everything the system was doing per time is being displayed. So you are getting feedback. That mode of operation is actually for the technician. It's not for the end user. The end user just want to hear, place your finger, remove the finger, you have been added, you are not added, rejected, accepted, whatever. That's what they want to know. Now, if you read all those other information it is sending to you, then you have more space. The program should contain a 16F84A. But with that number of information, strings being pulled out by the LCD, don't forget every character you are writing is taking your RAM space or your program memory space. Are you following me? So that was what led to the fact that the system will not sit comfortably or the program will not be contained in a 16F87CC. Do you get it? Even the 18F2620 that I use, I think I only use around 13% of the program memory space. 13%. But at the time I started developing with 16F84A, 87CC, the 24P92. At the time I was developing it, I got a point, it just told me I'm out of RAM. Not even, okay, I was first of all, was not programming, it was out of RAM. And then I changed where I was writing the program. I began to use more functions, and then it just told me I was out of program memory space. Do you get it? So the source of my computer is dependent on a lot of things. Now, if I was using the 16F876A, I might not be able to actually use baud rate at 4 megahertz crystal. I might not even be able to use it at 20 megahertz crystal. I'm not sure, but we can test it. But when I begin to use the 18F2620, even at 4 megahertz, it allows this baud rate. Did you get it? But again, I was not sure. I don't want to be caught off guard. I generally just put there 20 megahertz to be on the safe side. Do you get it? So the system of microcontroller will be determined by a lot of things. If you needed to use 57,600 as the baud rate, and it happens that your 4 megahertz cannot stand it, you might just increase your 4 megahertz to maybe 8, then maybe to 12, then to 16, to 20. If it happens that you still cannot stand it, what's the next thing? Choose a bigger microcontroller, and it might just happen that it will stand that baud rate. Do you get it? So we can say that the choice of this microcontroller, firstly or partly, is the choice of baud rate that we're working with. For other UART modules, what we usually do is that we connect it to the laptop, and then it has a way where we can actually reduce the baud rate. Are you getting it? It has a way where you can reduce its baud rate. So sometimes some of them require this baud rate, we sometimes have to drop it to maybe 9600, which any 4 megahertz crystal on the microcontroller, not running at high speed, will do. Don't forget, at 4 megahertz, you are still running XT, that's the crystal. From 4 megahertz crystal, you're now running what? HS, which is high speed. So that consumes more current. If you are using LP, which is low power, then your microcontroller or your system consumes less amount of current. Do you understand? That's the difference between the LP, which is the low power, the XT, and the HS. And don't forget, the HS is from 4 megahertz to what? To 20 megahertz. Do you understand it? All of that you set in your what? Your preprocessor directory. Hope I'm making sense.
Like, I want to understand the relationship between the baud rate and the crystal, because I know that this baud rate is based on the way it sends and
And
receives
saves, yeah, yes,
per
yes,
second.
yes.
Then while the frequency is based on how the cycles, the instruction per
time
and all that.
Okay, now the truth is, if you this is what you do. Get your microcontroller data sheet and go to the part where baud rate is discussed. There's a formula with which your baud rate generator. Pick up your data sheet and go to the part where it discusses baud rate. There's a baud rate generator in the controller that determines what baud rate you can use based on the crystal. For instance, let me give you the relationship. Remember how the crystal we use can determine what our refresh time will likely be, the maximum refresh time will likely be, or how our crystal will determine the maximum pulse-width modulation output that you likely get to have. See that relationship? The same relationship the baud rate has with the crystal you are using. Based on the crystal you are using, there are some values you cannot go above. So what do? You increase the crystal. Then you have some other boundaries you cannot exceed, or values you cannot use. Then you increase the crystal. But the issue is that even the microcontroller cannot even allow you to increase the crystal more than 20 megahertz. So if you look at it from all that we've discussed, from your microcontroller, you know that your RA0 down to RA5 already has your what? Your SD. You know that your ROB7 down to your ROB0 already has your what? Your keypad. So your RC, I'm not sure the bits would have your TSRX. And then you have one other indicator for change password indicator. So 3 was used for. So all the pins on A will use, all the pins on B will use, 3 pins on C will use. So this is 6 plus 8 plus 3. So how many pins will use? This is 9, that's 17 pins, isn't it? From the what? From the 22 mutable pin. How many is left? 5 pins were not used. Does it make sense? Does it make sense?
Yeah.
You get it?
You still use for maybe for
Oh, sorry, for the buzzer. There was one for the buzzer. Yes, sorry. Buzzer and then the relay. So take 2 from the 5. Okay, so 2 from there. That's 19. So only 3 was not used.
And I think you said the indicators, you used 2 indicators, not 14 passwords.
you know